Hi, welcome back. Here's the extension questions if you had a go at them. As always, the extension questions are optional and they're usually a bit harder. Go, slideshow, go. All right. Draw a force diagram for a magazine on a magazine rack. So my system is the magazine. And you'll see this magazine rack has a little bit down the bottom. So first thing I think of is that flow chart of, is it got a constant velocity or is it accelerating? It's definitely constant velocity of 0. So net force is 0. On book by Earth. There's a normal force because there's a surface there and that surface is going up at that angle. So that's there from this surface here. So that's Fn on book by the rack. And then there's another surface here. So there's another normal force going up this way. Now I don't know how big these are, but I know that when I draw my triangle, they've all got a, sorry, I don't know how big they are, but I know when I draw my vector addition diagram, which is going to be a triangle, that they all end up in the same spot. So I've just drawn them in any size here, but I know that when I might have to change the sizes of them to make it work with the vector addition diagram. It's another normal on book by, we'll just say the rack bottom, the bottom of the rack, just so you can see it's different. There's one F normal, and then the other F normal is up here. Great, that worked out. Perfect. All right. Draw a force diagram for a person, A, when they're stepping off, and B, when the stepping foot strikes the ground. This is tough. The reason why it's tough, and I might just talk about why it's tough and not go through the answer and just leave it. The reason is because even if someone walks at a constant velocity, and we model them walking at a constant velocity, if you look at their parts of movement, like when their foot lifts off the ground and then when they land again, this is speeding up. And then as they land, they slow down. It's a constant velocity average, but it's made up of bits of accelerating and decelerating. So that's why I've got these two sections here. I mean, let's quickly do the force diagrams for them then. But this is, you'll never ever get asked something like this, but this is a question, this is about thinking about how to apply physics to real life. And, you know, with some things like this, it's very simple, but other things, it turns out it's a little bit harder than you think. So they're accelerating this way. So this first section, gravity, there's a normal force going upwards. And at the point where they're speeding up, they have grip. So you couldn't do this, you couldn't walk forwards without grip. And what did we say? Grip that's helpful is called traction. So I'm going to put this as FF, friction, but I know really it's traction. So gravity on person by Earth, normal on person by ground, and this is a traction force on the foot by ground. When you put those together, you get F normal, F friction, F gravity. That's the total force. So at this point here, yes, they do speed up. and then when they hit their foot hits the ground, they slow down again. So that's this one. The other one over here is them slowing down, the acceleration's back. Force of gravity, force normal, and as you hit the ground, you can feel it. You can feel your foot sort of sliding forward in your boot as your boot grips, and that's a friction going back this way. So this one down here is a traction. This one up here is a friction. They're both a type of friction, but one that helps you to go forward is called traction, and one that helps you to go backwards is friction. But I'm okay with, I personally write them both as friction. And then when you put those together, you get something like that. Overall looks like that. Now, like I said, going into this is an ambiguous question. They never ask something as ambiguous as this. The questions they like asking in the exam are like this one. It's pretty obvious what the forces are, or like the skier here. But yeah, there's those extension questions done.